No. So welcome back, and today my objective is to talk about something which is a little new to you, in the sense that yesterday we talked about the SIA-based approach, and then we said that Irwin is a person who analyzed the stresses around the crack tip, and he could link whatever he wanted to say with the earlier development of Griffith. So that's how it is. And then in the presentation also, I started giving you the solutions that Irwin obtained for the stress strain distribution around the crack tip. And it's really something quite involved. And whenever you are going to a course, or you want to actually study a course on fracture mechanics, one cannot but have to know the solutions around the crack tip, or crack tip solutions for stresses and strain. And in fact, it involves certain considerations, certain new approaches which you may not have been exposed. So my job today in this session, and both sessions today, to talk about how the crack tip stress field around the crack tip stress field was obtained and how it was obtained. So just to give you, from scratch, what is stress analysis? That means we are interested in finding out for a given component or body, if it is in 2 dimensions, we can represent it as a thin sheet and having some boundary, and then you would have also some constraint on its movement, so which is actually shown in the sketch on the right hand side top. And you see that if you are trying to say that this is an elastic body of 2-dimensional in nature, and it has loading on its boundary as shown by the concentrated load at the top and some distributed load over a part of the boundary, and also some constraint on its movement, which are given by 2 pivots. So these are actually the general presentation of the body in 2-dimensional configurations for stress analysis. So what is that? If you wanted to find out the distribution of stress and strain inside the domain of this body, how do you go about it? What is actually way to go about it? And obviously you see that all that you try to seek for, we try to write the equations, everything, when you try to have a problem of the stress analysis, or even heat conduction, or let's say fluid flow, what you try to really aim at is that get the equation of flow, equation of deformation at a point in the body. That's how it is. And therefore here also it is the same thing, that if you are interested in finding out the stress strain distribution in the body of this nature, then we try to really look into the conditions that have got to be satisfied by the stresses at a point. What does that involve? It does involve that if the whole body is in equilibrium under the action of the boundary loadings and also its constraint, then obviously you see that this body is prevented from movement, but it is being subjected to loading, and therefore it will have to undergo deformation. It does undergo deformation, and those deformations are going to lead to development of stresses and strains. So therefore, in a sense, that we want to find out the deformation of the whole body, or deformation at every point of the body, and at the same time we would also like to obtain the information about the stress and strain at every point of the body. So how can we actually do that? Obviously, first of all, you see that if you are trying to talk about the deformation, obviously what it means is that if its rigid body motion is prevented, then in that case it is going to deform. That means every point, every dot on the body is going to have some displacement in the x and y directions. And therefore, to find out the deformation of the whole body, it is necessary to find out the value of the displacements at every point, multitude of points, millions of points which constitute the body by some way. And that's what the job. So once you get the deformation, then obviously from that deformation, we can find out the strain, and from strain, we can find out the stresses. This is one way. Alternatively, if somebody can find out the stresses at every point in the body, then one can really find out the strains, and then one can find out the displacement. So these are the two ways of going about it. But here you see that if the we'll go this way, that we'll try to consider the body is in equilibrium under the action of external forces and also constant movement. And therefore, if we now consider an element, an infinitesimal element of size delta x by delta y, and thickness, of course, let's assume it to be constant, then what happens is that the stresses that comes out, these are the stresses, you see, at infinitesimal element of size delta x by delta y and of constant thickness, and it is going to be actually, this whole body is in equilibrium. Therefore, even that small element that you have segregated from it, it is also going to be in equilibrium. Means what? That means this element of size delta x by delta y, it is actually subjected to some stresses on the boundary of it. And the right hand side vertical face, you see, that's the face actually of size delta y, and it is called x face because its outer normal is directed in the positive x direction. So on the x face of the element, I can have two stresses. One is normal stress, which is indicated by sigma x plus delta sigma x, and there will be also shear stress, parallel stress, which is tau xy plus delta tau xy. Or maybe let me put it this way, let us take the left hand edge, which is actually whose outer normal is directed in the negative x direction. This x face, which is subjected to stress sigma x and tau xy, normal stress sigma x and shear stress tau xy. And if we now go to the right face, you see we have moved by delta x. Obviously, the stress sigma x is not going to remain constant, it's going to change by some small amount. That is sigma x plus delta sigma x. Tau xy, which is shear stress, on the right face it will have different value because you have moved the distance of delta x, and therefore the value of the shear stress is tau xy plus delta tau xy. So these are the stresses on the two vertical faces. Exactly the same way, if you try to take the bottom face, the stress is going to be, normal stress is sigma y, shear stress is tau xy, and on the vertical, the top face, which is actually in the which is at a distance of delta y from the bottom face, its stresses are again normal stress sigma y plus delta sigma y, which has increased, and similarly shear stress has also changed, which is tau yx plus delta tau x. Yeah, you see that this is something, this double initial notation. It is better to understand what is the double initial notation. See, we are using for normal stress, it is generally double subscript is there. So let's say on the left hand face sigma x, it is indeed sigma xx. X stress in the x direction, that's why it is sigma subscript xx. But it is common practice, for normal stress, we don't write both the indices, we write only the first index because they are repeated. Shear stress, obviously it is acting on the x face, it is in the y direction, and this is tau x is the face identification, y is the direction identification. So this is how all the stresses are identified, thereby one can understand what is the face on which it is acting and which direction it is acting. So all these stresses that I have shown on this element of size delta x, delta y, they are positive stresses. And you can imagine or you can think that this element has been taken off the whole body and it is subjected to stresses by the rest of the body which are indicated there. And as a practice, or it is expected that since the whole body was in equilibrium, no movement, similarly this element that also we have segregated, it is in equilibrium. That means what? The stresses that are applied on this element delta x, delta y by the rest of the body, they are in a position to keep this element in equilibrium. It does not actually have any inequilibrium, or it does not have any extra force which is going to give rise to any movement. So that's all. So these are the stresses in the body which is in static equilibrium, and it is subjected to this element is subjected to stresses by the remaining body by the stresses which are indicated. So these are the forces which are acting on this element. Now there are also possibility of some other forces which I have shown on the sketch. The stresses are there on the boundary faces, but this element can also be subjected to body forces or volumetric forces. And it comes up, that if you are trying to think of a plate hanging, so it will have gravitational forces, and these gravitational forces will have component in your selected Cartesian direction x and y. So in this case, it can have force in one direction, it can have force in both directions. They are indicated. So these forces that are coming externally on this body or this element delta x, delta y are the stresses about which we have talked about. But there can be also volumetric forces or body forces, which depends on the volume of the body, and they are actually, it can be the gravitational weight, which depends on the volume of the body or volume of the element. It can have another source of origin. When I think of it, that when a grinding wheel is rotating, or actually a grinding saw, I beg pardon, when a saw is rotating or a shaft is rotating, you see that if you take a slice of that, it is actually every point of the body is subjected to forces because of rotation, which are centrifugal forces. And this centrifugal force will have components depending on your selection of axis. It can have two components, it can have one component. So in this case, we have represented those volumetric forces or body forces by two components, capital X and capital Y in that element sketch. So X is per unit volume, capital Y is also per unit volume. So therefore, finally, in a general problem of 2 dimensions, you are going to have stresses on an element which are indicated by the components of stresses on the 4 faces of the element, plus body force per unit volume, that is capital X and capital Y. So that's all. And now, if you try to consider the equilibrium of this body or element, delta x, delta y, the first equation that you write will be the force acting on the positive x face, where stresses are sigma x plus delta sigma x, and tau xy plus delta tau xy. Those are the 2 forces. And on the negative face, where stresses are sigma x and tau xy. So therefore, you see that these stresses will give rise to some resultant force in the x direction. And similarly, the stress which are acting on the top and bottom face, their shear stress component, they are also going to give rise to some net force in the x direction. So those can be written, and finally when you go for simplifying it, then you get the equation which finally means that equilibrium equation, sum of the forces of this element in the x direction will give you the final equation delta sigma x delta x plus delta tau xy delta y plus capital X equal to 0. So this is the equilibrium equation at the point in the x direction. By similar type of considerations, you could take up the forces acting in the y direction. So all the forces like sigma y plus delta sigma y at the bottom face, and shear stresses tau xy plus delta tau xy and on the left face tau xy. So if you try to take the sum total of the forces and try to make it equal to 0, this will give you an equation which is in the second line, delta tau yx delta x plus delta sigma y delta y plus capital Y equal to 0. So this is the equilibrium equation on the y direction. And this element must also be in rotational equilibrium. If you try to take the rotational equilibrium, that means moment of all the forces above the center point of the element, that will give you finally the equation tau yx equal to tau xy. That means stress on the vertical face is really equal to stress on the horizontal face. This is something also quite interesting. The stress on the vertical face is tau xy and stress on the horizontal face is tau yx. These two are equal. So therefore there is no difference between tau yx and tau xy can be found. So finally, in this equation, the unknown stresses are nothing but sigma x, sigma y, tau xy. Three stresses are the unknown. Yeah, I think let's spend little time on this. What it means is that when a body is deforming, the stresses are 4 in number, sigma x, sigma y, tau xy, tau yx. But because of the deformation pattern that tau y is equal to tau xy, these two shear stresses are the same. Finally, therefore, independent stress components are sigma x, sigma y, and tau xy. So for any body in 2 dimensions which is undergoing deformation, it will have 3 stress components as unknown at every point, sigma x, sigma y, and tau xy. So therefore, you see that to find out the stress distribution in the whole body, what you need to find out that sigma x as a function of xy in the whole body, sigma y as a function of x and y in the whole body, and at the same time tau xy as a function of x and y in the whole body. So that's the problem of stress analysis. So for the problem of stress analysis, what you need to do is that you have to find out 3 functions, tau xy, sigma x, and sigma y. Both are all these are functions of stress coordinates x and y. So therefore, stress analysis in 2 dimensions means you have to find out 3 stress functions, sigma x, sigma y, and tau xy, each of which are functions of x and y. That's it. That's the problem of stress analysis. So if it is in 3 dimensions, then in that case, you see, you will have x plane, y plane, and z plane. For each of the planes, you will have 1 normal stress and 2 shear stresses. And therefore, you will have 6 stresses. Stress functions as unknown. Each of them is a function of coordinates x, y, and z. And one has to find out 6 stress functions in the 3 dimensions. 3 stress functions in 2 dimensions, 6 stress functions in 3 dimensions. This is the problem. And you see that you are not talking of finding out just 3 unknown parameters, 3 unknown functions. Each of them are functions of x and y in 2 dimensions, x, y, and z in 3 dimensions. So that's the type of problem of stress analysis. So for problem of stress analysis in 2 dimensions, one needs to find out 3 unknown functions, sigma x, sigma y, and tau xy. So you can imagine the enormity of the problem, that you have to find out really 3 stress functions. And to find out them, what is the way out? You have already established that these stress functions are going to satisfy these 3 equations. And again, I want to link some idea that you have already had with this position that is there. You have to find out 3 stress functions from 2 equilibrium equations. That you see, you have already got 3 stresses as unknown, sigma x, sigma y, and tau xy and tau yx, but we have been able to establish that tau xy is equal to tau yx. So therefore, all those 4 stress functions are there in the equilibrium equations, but two are the same, and therefore finally we have three stress functions to be found out. And now the question is, this we have two equilibrium equations. Look at this, we have two equilibrium equations. That equation, first equation and the second equation on the screen, and we have to find out three unknown functions, sigma x, sigma y, and tau xi. So this problem is statically indeterminate. Your unknowns are three, but you have two equilibrium equations. So therefore the problem is statically indeterminate. Have you come across problems of statical indeterminacy? Have you? You have actually had problem of statical indeterminacy in statics. You had, because you see that if you try to say that it is a simply supported beam with two supports at its end, then you see that you have two unknown reactions as they, two reactions, support reactions as unknowns, and but then you see that you have two equilibrium equations. What are they? So it's a simply supported beam, horizontally oriented, with support in the vertical directions. There, you try to say that two reactions are there. Sum of the two reactions is equal to external load. That is the statical equilibrium equation. And you have two unknowns and one equilibrium equation. But at the same time, you can take moment of all the forces acting in the vertical direction about any point on the beam. That will give the third equation. So therefore, although you have two reactions, you have one equilibrium equation, but then this moment equilibrium, that will give you the second equation. So you have two equations, two unknowns, two static equilibrium equations and two unknowns you can find it. That is statically determinate. But if you think of it, that let's say we have, let's say that it is actually simply supported beam with fixed end, one fixed end. So in that case, you see that you have obviously two end reactions will be there, but also there will be a moment at the support, that fixed support. So therefore the problem becomes statically indeterminate. Three unknown reactions, but two equilibrium equations. So therefore you cannot solve it, statically indeterminacy. So here also it is in the same way. In this problem, you see that we have three unknown stress functions, sigma x, sigma y, and tau xi, but then we have two equilibrium equations. The problem is statically indeterminate. So this problem is statically indeterminate. Then how do you overcome? We overcome that. How was it done in the case of strength of materials? In the case of strength of materials, that even if you consider the, let's say, that problem of propped simply supported beams, one end is fixed, other end is just simply supported, then in that case you see that what we can think of doing, we have to find out two vertical, two reactions at the two ends plus the moment. So therefore three unknowns. So what we do is that we try to find out extra equations to overcome this statical indeterminacy. What is that extra equation? We try to, we have to bring in the deformation condition in some way to bring in another extra equations. Like this, you see that in the case of, let's say, cantilever, if it is a simply supported beam, but one end is actually built in, it is not allowed to rotate. So then in that case, we can get the extra equations by considering that the beam is supported at the two ends by vertical forces, but at the same time, one of the end of the beam is not allowed to rotate. If it is fixed, it is not allowed to rotate. So that deformation conditions, that another action of all the forces acting on the beam, it does not rotate at the built-in end. So therefore that deformation condition is actually what is extra. We try to adopt and get another equations to overcome this statical indeterminacy. So here also, what we are going to do, that we have two differential equations, but we have three unknowns. So therefore what we have to do, we have to find out extra equations by considering the deformation. So let's see what is that there. And sometimes this deformation condition is called compatibility condition. In the case of that simply supported beam with fixed end, we try to consider that beam does not rotate at one end, so therefore its rotation is zero. So therefore that is a constraint on the deformation, and that's what is the way to find out extra equation. So we have to find out extra equation, and these are obtained by considering compatibility condition, what sort of deformation existing in the system. So compatibility conditions, that how do we get it? Now we know that epsilon x is a, let's say, normal strain, which is nothing but delta u delta x. Epsilon y, is delta v delta y, and shear strain, I'm sorry, shear strain is nothing but gamma xy equal to, sorry, what is that? Yeah. And shear strain is delta u delta y plus delta v delta x, so cross derivative. And now you know that if I just try to differentiate left hand side 2 times with respect to x and y, and similarly if if I differentiate left side by 2 times with x and then y, left is this, right side is going to give me equation of that type. And now if we try to write the expression for strains in terms of stresses, gamma xy is nothing but delta, that it is written at the top, and shear stress is nothing but rigidity modulus into the shear strain. So if I write that, that this left hand side, it comes out in terms of stresses, it is 1 by mu, mu is rigidity modulus, is nothing but it is nothing but 1 by mu delta 2 tau xy delta x delta y left hand side, and right hand side delta 2 delta y square epsilon x is nothing but, it can be written as sigma x minus y, nu times sigma y by e. So this epsilon x is nothing but sigma x by e minus nu times sigma y by e. So that's the epsilon x. Epsilon y is nothing but sigma y minus nu times sigma x by e. So all this actually in terms of stresses. So we are writing the strains in terms of stresses. Finally, this gives us a relationship involving 3 stresses, sigma x, sigma
Sir,
x.
excuse me.
Yeah.
Yeah, there was a message saying that the battery of your PC is low.
Oh.
Please switch on the charger.
Oh, I have to put on, bro?
Yeah, you have to connect it to the power supply.
That's right. Thank you so much.
No problem.
Oh, it is 88%. It is 88%. Sachin.
I saw the message actually, and there is a symbol of battery in the lower tray right side. That is also flashing.
Okay, anyway, I put it on. Can you hear me properly?
Not, not the phone, the laptop I'm saying.
Laptop ka.
Yeah, see.
I think it's disconnected.
Yeah, Professor Maiti is restarting. Just a minute. Wait a minute.
Wait for a few minutes. Yeah, fine. Sir, your mic is mute. Go to yes. Now it's on mute. Fine.
Present now.
Yes, yes. Google Meet present now. Yes, fine.
Yeah, you have to open your presentation, sir.
Yeah. It's okay?
Yeah, it's okay.
It's now all right, no?
Yeah, fine, sir. Thank you.
Yeah. So we were going that way, right? Yeah, this was the compatibility question we were talking, right? Hello?
Yes, sir. Yes, sir.
You can hear me, right?
Yeah, I can.
Oh, fine. So therefore, that's good. So we were actually trying to we have come to this point that your compatibility equation, that deformation takes place in such a way that it satisfies the differential equation which is there in the second line or third line from the top. And if you write the same equation in the form of stresses, it gives you an equation which is number 3 written there at the bottom of this screen. So therefore, you see that finally what has happened, the problem of two-dimensional stress analysis was in the form of two differential equations involving 3 unknown functions. But by making use of the compatibility of deformation, that is shear strain is related to the displacement and deformation in the two directions, x and y, we get the relationship again in terms of stresses, which is the equation number 3. So finally, you see, that we have three differential equations, 1, 2, which were shown to you earlier, one which is involving two equations, and then third equation which is numbered there. So these three equations, you see, all these three equations involve three stress functions, sigma x, sigma y, and tau xy. So three stress functions, and you have three equations, so therefore it is solvable. And therefore, you see, stress analysis problem in 2 dimensions indeed is nothing but solving these three differential equations, and that's the core problem. It is certainly a very complex situation. You have three partial differential equations of the three stress functions of two coordinates x and y. So it is difficult, you see. So when we have considered that there are no body forces, then you know that these three equations again can be combined into this fourth equation. So therefore, one can think of it that you have sigma equation number 1 and 2 and then 4. That is the third equation, which is again giving you three equations to solve for three stress functions. Alternatively, you have to think about equation number 1 and 2 and number 3. So this will be the problem of stress analysis in 2 dimensions. So you have to find out three stress functions. And you see that these three stress functions to be obtained from three differential equations, although they are simple, it is not that simple, it is quite difficult, and some ways are there to solve it, but then they are really involved. So some mathematicians, you know, they thought about, they sat down and they tried to think of, can that be simplified? So one mathematician, English mathematicians, what he said, that you see these three equations are there, 1, 2 and number 3. These three equations, finally, you know that it can be simplified. So we know that we have to satisfy the equilibrium equations plus the other equation, which is the compatibility equation, and this compatibility equation it can be again actually simplified in the format grad square sigma x plus sigma y equal to 0. So that is possible. So what one English mathematician, he said that, you know, he showed that if we write the stresses in this form, that sigma x stress in terms of delta square phi delta y square, sigma y as delta square phi delta x square, shear stress tau xy delta 2 phi delta x delta y. So if you bring in one single function of x and y, and if you write in this form, then in that case, this problem of determining the stress field is equivalent to determining these three stresses. Alternatively, it is just determining the function phi as a function of x and y. So please note this, that, you know, he made the problem much simplified. That problem of two-dimensional stress analysis boils down to determining a function phi, which is a function of x and y, wherein this phi function, how to determine this phi function? Indeed, actually, from equation number 4, with this definition of sigma x and sigma y, you know, it comes out like this. It is nothing but grad square, which is delta 2 delta x square plus delta 2 delta y square phi. So if you just try to write this, that this compatibility equation is nothing but grad square sigma x plus sigma y equal to 0. You see that that is the compatibility equations. And the other thing that is there is this, that if you write the value of sigma x, sigma y, it becomes like this, grad 2 phi equal to 0. So that's this is known as biharmonic equation. So grad 2 phi is biharmonic equation, and in this case it becomes biharmonic equation, grad 4 phi equal to 0. That phi function, which is a function of x and y, it is actually just a function of x and y, and it must satisfy that. So therefore, you see that your stress determination for a particular problem, it is simply solving this biharmonic equation subject to satisfaction of stresses specified at the boundary. So you have to take this phi function such a way that it satisfies the stresses specified at the boundary, where stresses are given. Sigma x is delta 2 phi delta y square, sigma y is delta 2 phi delta x square, and shear stress is minus delta 2 phi delta x delta y, delta 2 phi minus delta 2 phi delta x delta y. So that's how the problem has been actually converted in this form, and which is the actually final position that two-dimensional stress analysis involves determination of phi functions, where your phi function is such that it satisfies the boundary conditions in terms of stresses, and then it should also satisfy the biharmonic equation. So that's how it is. But then unfortunately, that this problem is simple, and it here simple, but then to find out the solutions, it's not always simple to find out that phi, but then there are certain steps which can be taken up to find out this phi, and that is actually based on complex variable formulation, and it was actually given by Kolosov and Muskelis-Billy. And I think I want to tell some sort of scoop about these two names. Muskelis-Billy was a professor in Russia in some mathematics department, and Kolosov was his PhD student. So this formulation was actually the outcome of thesis of Kolosov under the guidance of Muskelis-Billy. So that's why it is known as Kolosov-Muskelis-Billy formulation. And it is based on analytic function or holomorphic function regular function. So I think some of you have come across complex variable, and in complex variable, what you have a function of x and y, which can have actually real part and imaginary part, and this both real and imaginary part, they are having, when they have a feature that they satisfy the Cauchy-Riemann condition. This is the Cauchy-Riemann condition. A function which is complex variable based, it will have real part and imaginary part. And this real and imaginary part, if they satisfy the conditions that delta real part fz derivative with respect to x is equal to delta imaginary part of fz derivative with respect to y. So if these derivatives are equal, similarly the other relation is that real part of fz differentiation with respect to y is minus imaginary part of fz derivative with respect to. So these are Cauchy-Riemann conditions. So these Cauchy-Riemann conditions satisfaction also gives rise to condition that both the real and imaginary part of this function, this complex function, they satisfy Laplace equation. So therefore, you see this real part of analytic function or complex function fz, imaginary part of complex function fz, they are both satisfying Laplace equation. So when you have this condition, this function fz is called analytic function or holomorphic function, regular functions. And indeed, it means physically, it means that these functions have continuous derivative all throughout the domain. That's the thing. They are continuous functions, and they have derivative also continuous all throughout the domain. So that's the other manifestation of these functions. So these real and imaginary parts are going to be both what you call that Laplace function. Laplace, they satisfy the Laplace equations. And examples, you see that examples are these analytic functions, they can be easily written by having terms like z, z square, z cube, z4, z to the power n. All these exponential functions in terms of z, they are actually analytic functions. So therefore, you see that you can write the analytic functions very easily, and therefore it is convenient to write the stress functions in the involving these functions. I think that let us quickly look into, let's say, z square. We write a analytic function as z square. What does it mean? Z is nothing but x plus iy square, and if you expand it, it becomes actually x square minus y square plus twice ixy. So therefore, this analytic function has real part x square minus y square, and the imaginary part is 2xy. So therefore, both the parts are there, and if you see quickly that this both real and imaginary part, they satisfy the biharmonic equation. So if you try to think of this real part x square minus y square, and if you try to write that delta 2 real part delta x square plus delta 2 imaginary part delta y square, if you try to actually take that combinations, it will satisfy that Laplace equation. Similarly, if you try to take the z to the power 4 another example of analytic functions, that will give you real part x4 plus y4 minus 6 times x square y square plus I times 4 x cube y minus xy cube. So that's how it is. They are all functions of x and y. So these are readily available, and you can just make combinations of them to write solutions for your problem. Okay, so this is the complex variable approach, but we have got another thing to also link here, that I said that English mathematicians who said that write sigma x is equal to delta 2 phi delta y square, sigma y as delta 2 phi delta x square, then the three equilibrium equations, they really get easily satisfied. So if you write the stresses in terms of this phi function, and this phi function was introduced by Airy, and it is called Airy stress function. And if you write the stresses in terms of this Airy stress function, sigma x is delta 2 phi delta y square, sigma y delta 2 phi delta x square, tau xy is delta 2 phi minus delta 2 phi delta x delta y. You will see that if you plug in these values in the equilibrium equation, delta sigma x plus delta tau xy delta y, if you sum up, that will become 0. Similarly, delta 2 tau xy delta x square, delta 2 xy delta x plus delta sigma y delta y, you will sum up them, it will become 0. So equilibrium equations are automatically satisfied. And finally, if you want to find out this phi function, you have to really go back to that compatibility condition, which is this. So to find out phi, herein actually you have to find out phi which satisfies this equation. So this was the other way of going about it. Now we have already talked about Airy stress function. Now we see that it was later shown by Kolosov and Muskeles-Billy that you see that you can write this Airy stress function in terms of two analytic functions. What is the two analytic functions? Fz and chi-z, chi. So Fz and chi-z, we try to introduce two analytic functions, and this Airy stress function, if we define by that relation, that real part of z bar fz plus chi-z. So this, if we write in this form, then in that case, you see that we get the Airy stress function, and therefore we can get this relationship sigma x plus sigma y equal to 4 times real part of fz, and sigma y minus x plus 2i tau xy is equal to this. So these are again actually given in terms of that two analytic functions. And also it is possible to show that displacements u in the x direction, v in the y direction is given again in terms of the two analytic functions fz and chi-z is given here. So that relationship was also readily available. So finally, that with this analytic function approach, we have two analytic functions which can be easily written as function of x and y, but then we have also the benefit that If I do that, then sigma x, sigma y are actually linked up to the derivative of these analytic functions, and sum of the two normal stresses is given by the first derivative of fz, and sigma y minus sigma x plus 2y tau xi is given by this relationship, double derivative of the two analytic functions. And at the same time, it was possible to come to this relationship to show that the displacement, so you have got the stresses by these two expressions, and the displacements u plus iv is equal to 3 minus nu by e fz minus 1 plus nu by e z into f dash z over bar, that f bar first derivative z bar. So this function, this is also called f z over bar, f dash base z over bar, and then 1 plus nu chi dash z over bar. So this has under plane stress condition. And at the same time, if you take the boundary condition, say part of the boundary from A to B, because of the distributed stresses, you will have some net load on the portion AB in the x and y direction per unit length. Then in that case, it was also possible to show that fx is nothing but delta phi delta y derivative value at B minus value at A. Fy is minus first derivative of phi with respect to x, value of this derivative at the point B minus A. And at the same time, moment of all these forces about the origin of the coordinates O is going to be given by this relationship, which is again in terms of air stress. So that's how it is. So therefore all these actually conversions are also easily derivable, and they are given finally, and it's I'm just trying to show you the dotted way of going. So you see that again, if you transform the coordinate, if you rotate the coordinate by theta angle, then the displacement will be u theta in the radial direction, d theta in the tangential direction. Then the derivatives are also related to the value of displacements in the u theta coordinate or r theta coordinate is related to displacements in xy coordinate by these relations. And stresses in the new coordinates are also related to the stresses in the original coordinate x and y. So that's how. So these are actually some of the relationships are also available. So that is it. So this is the basis, you know, that this stress function approach of Kolosov-Muskeles-Vili or Rayleigh stress function is the basis of finding out the solution for stress distribution in the elastic body, and it gets facilitated by this Kolosov-Muskeles-Vili potential formulation if you have crack problems. And some more refinement was done, that this Kolosov-Muskeles-Vili formulation, you know, that when there is a let's say plate with a circular hole and it is subjected to internal pressure, so it is called actually bearing problem. So if you have a plate with a circular cutout and the loading on its boundary in the radial direction, it is a problem of symmetric, double symmetric problem. The stress distribution is symmetric about the x-axis and y-axis. And exactly the same way, if you have a problem of crack, if you have a rectangular plate and it is loaded in the x and y direction by the uniformly stress distribution on the x face and y face, then this is also a problem, the double symmetry. The stress distribution is symmetric about the x-axis, symmetric about the y-axis, and therefore this sort of problem, you know, it was shown by Westergaard that these double symmetric problems, you know, they give rise to some simplification possible, and we can find out the stress distribution very easily, and therefore that approach is known as Westergaard stress function approach. So it was actually indicated as Westergaard stress function approach. So this is what it is. So he gave the approach, and it's very convenient for crack problems. So therefore he finally established that when you have double symmetric problem, you don't need two analytic functions. you can write the solution for the problem considering one analytic function, just fz. You don't need xj. So in that case, the stresses are given in terms of that single analytic function fz. Sigma x is nothing but real part of fz minus y imaginary part of first derivative of fz. Similarly, sigma y is also having similar form, and shear stress is given by minus y f dash z. So this is how it is. So therefore, we have now come to the crack problem, that we have a plate with a crack, and then it is subjected to loading at the outer boundary, uniform intensity of stress at the on the x and y boundary of sigma. So then in that case, this stress function that can be written for this problem, it is obtained by Westergaard, and he said that you don't have to do much. You simply actually make use of one analytic function, and that analytic function has the form fz equal to sigma z divided by square root z square minus a square. So what are the coordinates? Please just have a look at it. So it is like this, that to have this problem, we must consider these coordinates. So this is the problem. So in that case, you see that plate is infinite. So therefore, both x and y, the value at the boundary is infinity. Therefore, we can say that z tends to infinity at the boundary. That's the problem. And it has a crack at the center. Origin is at the center. And there is a crack of size 2a. And this is the type of external boundary loading. Then the question is, what are the stresses around the crack tip, at the tip of the crack, where crack tip is located at x equal to a and minus a. So that's it. So we would like to look into solution for this problem with this approach, and therefore I'll actually try to have your attention to understand this. So we are trying to solve for mode 1 problem, wherein the stress function, Westergaard stress function, is only required to find out the solution for the distribution of stresses and strain in the whole panel with the crack of size 2a, and its center is at the origin. So that's the stress function. So fz is equal to sigma z by square root z square minus a square. In fact, you know that this stress function, you will say that what is the guarantee that this is the really solution to the problem? So, you know, this is natural question that one would like to ask, that what is the guarantee that this is the stress function of the problem? I think that, you know, some of you who has done PG courses on stress analysis, they have come across what is known as uniqueness theory. Uniqueness. For a problem with given boundary conditions and loading, there is only one solution. There is no question of duplicity possible. So, uniqueness theorem is the basis to check the what you call that suitability or the exactness or correctness of this solution. So I would like to actually show you that. So you see that if z is the function which defines sigma stresses sigma x, sigma y, and tau xy, then in that case you see that my sigma x stress is what? Sigma x stress is given. We have already defined that sigma x stress. Westergaard actually defined that sigma x is real part of fz minus y imaginary part of f dash z. Similarly, sigma y, thus that minus is plus, and tau xi. So therefore, this only that sigma z by square root z square minus a square, that defines fz, and these are the stresses. So therefore, let us see that this is the solution to the problem. So for doing that, what I will do, I would like to actually now consider whether the first equilibrium equations involving sigma x and tau xi, which is nothing but delta sigma x delta x plus delta tau xi delta y equal to 0. So we will now try to see delta sigma x delta x plus delta tau xi delta y. So therefore, you see, what does it mean? This is delta delta x, real part of fz, plus delta delta y minus y real part of f dash z, that is sigma x, that is tau xy. So these two things added up should be 0. So if I go on doing this, I've already got the definition for fz and this. Therefore, all this can be written, and if you write, so therefore this will give you, you see, it will give you real part of first derivative of this one, and then minus y, because this sigma x is actually nothing but sigma x is this one, yes. Sigma x is real part of fz minus y imaginary part of f dash. So delta x means we have to take the derivative of fz with respect to x, and this one is again derivative with respect to x, so that will now be 0, so that's gone, and therefore we will have y imaginary part double derivative of f dash z with respect to x, so it is double derivative. Similarly, we have delta tau xy delta y, that means I have to take the derivative of this product in terms of y. So all that if I do, then it gives you finally, this expression. So that's what I have written here. And if I plug in the value, so it will become real part of f dash z minus y imaginary part of double derivative of f dash z minus this is a real part of f dash z plus this is actually y imaginary part of it is derivative with respect to y, means I will come, that I square will make it positive f dash z. And look at this. You see these two terms cancel, these two terms cancel. Finally, the value that comes out to be 0. So the first equilibrium equation is satisfied by this function that we have invoked. Similarly, it is easy to show. You take the second equation of equilibrium, which is nothing but delta tau xy delta x plus delta sigma y delta y. If you again put in the value of these functions and then take the derivative, and again you will find that this right hand side will continue. So therefore the two equilibrium equations are satisfied. Hence, when the two equilibrium equations are satisfied, that is one part of this checking of the function. Second thing that we have to check, that this definition of the function, it must satisfy the boundary condition. Not only the stress conditions or equilibrium equation, but also the stress boundary condition. What are the boundary stresses? You see, in the case of this problem of infinite plate with crack and stresses sigma x acting on the x face and sigma y acting on the y face, and what are they? They are all actually both are sigma. So therefore that condition is there. Let us check whether this sigma x is sigma at z tends to infinity. Sigma x definition is this, and if I try to take this definition and consider the boundary z tends to infinity, once you plug in the value, you see that if you look into this, what they are going to give you. Finally, you see that it will give you this one remains as it is, and this one y and its derivative with respect to z means actually it is going to give you this derivative, because fz is sigma z by square root z square minus a square, and if you take its derivative with respect to z, it gives you this. At z tends to infinity, this gives you just sigma, and because this you can take it down, and it will actually have 1 minus a square by z square. At z tends to infinity, this is 0 and this is 1, so therefore this becomes actually sigma. Whereas in this case, you see, in this case you will find that these two terms at z tends to infinity, these two terms will become equal, it will become 0 automatically. Finally, this will give you sigma. So therefore, both sigma x stress is sigma, and also sigma y exactly by the similar consideration at z tends to infinity, stress is sigma. So that the two boundaries, the stresses as required, they are actually there, and therefore this is the exact solution to the problem. And there is also another boundary where you have to check the stresses. This is something, please note what is this boundary condition. In the case of a crack with this type of thing, You see that crack faces, the top and bottom face of the crack which is located at origin, spanning from -A to +A, there is no normal stress on the crack faces, and there is no shear stress on the crack faces. These crack faces are stress-free, both sigma normal stress and shear stress is 0. So this solution that you have got, it must ensure that yes, their crack faces are stress-free. So if you want to check that, so that is also to be checked, and I have checked it here and I will show you. So proof of boundary condition on crack faces, sigma y equal to 0. You see that sigma y in terms of here is that Westergaard function, these are the stresses. And if you try to say crack face means y equal to 0, so if y equal to 0, that means actually z is x plus iy, y is 0 means it will become sigma z is x, and here y is 0, so this part gets knocked out. So sigma y is simply this one. And its expression for on the x-axis y equal to 0, that means z is only x. So therefore y stress is real part of sigma x by square root x square minus a square. And you must remember that crack faces are where the value of x is always actually less than a. So this is negative. So therefore you see that this indeed it means that sigma is nothing but this one. So this is always actually x is less than a. So therefore this is taken out. So this minus sign gives you I, and therefore this is what it is. Now, what is it? This one is the real part. So here these are two real quantities, no imaginary value, and this one is I is there. So therefore I will go up. So it will become actually real part of imaginary quantity is 0. Therefore stress is 0. I want to repeat again. See this sigma that we are calculating. What is its value? It is real part of sigma x by x square minus a square. Only crack faces x is always less than a, so therefore it is a negative quantity. So I just rearrange this a square minus x square, which is now positive, and that minus 1 square root is I, so therefore it is this quantity. And now this, you see here, this is real, this is also real, and this I is there, so it will become minus I x by this quantity, and real part of this imaginary quantity is 0, so therefore stress sigma y is 0. So it shows that the crack faces are stress-free, normal stresses are not there. So exactly the same way, if we try to take the shear stress on the crack faces, it would also give you the same position that these shear stresses on the crack faces are also 0, and therefore that all the boundary conditions of the problem of mode 1 crack is satisfied. So therefore this is the solution to the center crack problem in an infinite plate with biaxial. So therefore this is what by the stress function. Then in order to find out the expression for sigma x, sigma y and tau xy, we have to do some manipulations. So that manipulation is being done here. Sigma x is this, and your value of function fz is already there, and therefore if you put the value of all this, it will give you this expression. So yeah, it will actually see. We'll now try to get the crack tip solutions. How do I go? Sigma x is given by this one, that expression for stress is here. So I would now like to, and this is the solution when origin is at the center of the crack. But I would now like to shift the origin to crack tip, which is at z equal to a. So therefore, z equal to a is the, I would like to shift from the center to the crack tip. Then in that case, I have to make this substitution. Z is approximately equal to a when r is very, very small compared to the crack side. And z minus a is r e to the power I theta. So if I do that, sigma x actually with all the substitutions, it gives you this value. and sigma x is nothing but here square root a cancels, so therefore sigma root a by root 2 r e to the power minus I theta, and then this thing, this term, this portion would become this, and therefore subsequently if I just go on simplifying, this is real part of e to the power I theta by 2 is nothing but cos theta by 2 r sin theta sigma root a by 2 into root 2r e to the power minus I3 theta by 2. So therefore this will give you sigma root pi a by root 2 pi r cos theta by 2 plus sigma root pi a root 2 pi r cos theta by 2 sin theta by 2 minus cos 3 theta by 2. And finally, you just do little more simplification. It gives you sigma root pi a by root 2 pi r cos theta by 2 1 minus sin theta by 2 sin 3 theta by 2. Similarly, sigma y, it has similar expression. It will come out to be sigma root pi a root 2 pi r cos theta by 2 into 1 minus sin theta by 2 sin 3 theta by 2. Similarly, your tau xy is nothing but y re f dash z. So if you do substitution and little bit of manipulation, again you substitute that z is approximately equal to a, z minus a is r e to the power I theta. So if you do all these, you see finally it will give you this expression, and which on further simplification it gives you sigma root pi a root 2 pi r sin theta by 2 cos theta by 2 cos 3 theta by 2. So finally you see that we have got the solution for the crack tip stress field in terms which was earlier presented, yes, the last time I presented, which was obtained by Irwin. So this is how it is, that crack tip solution was obtained from the consideration of stress function. That stress function, initially we were talking about Airy stress function, then we talked about analytic functions, and then writing the analytic functions, looking at the boundary conditions, we got that stress function in terms of sigma z by square root z square minus a square, and then subsequently when I plug in the value of that stress function in the expression for sigma x, sigma y and tau xy, we got the value of the stresses around the crack tip as r tends to 0. Please remember, this stress field is correct only when r is very, very small. It is not that it is actually going to be valid everywhere. It is with the consideration that you are talking of the stresses very close to the crack tip within a small circle, which value is very, very small compared to crack size 2a. And indeed it is about 5% and less of the crack size a, that this stress function, this solution is valid and it is accurate. So that's how the stress distribution around the crack tip in mode 1 was obtained. Yeah, so we have been able to get the stress field. Now the question is, we have to obtain the displacement field also. In the case of crack tip field, it is not only that sigma x, sigma y, tau xy are important, it is also important to find out the displacement field. How do we get the displacement? I think let me just pause for a few minutes, then we'll get started for the next displacement part. So obviously, that this I have gone little faster here, and I have really presented many things before you. So just to summarize what I talked about. Initially, I started talking about the real problem of stress analysis. What does it mean in the case of 2 dimensions and 3 dimensions? If you are interested in doing the problem of stress analysis in 2 dimensions, you have to find out the 3 stress functions or 3 stresses as a function of space. In the case of three dimensions, it will be 6 components of stresses in 3 dimensions. So therefore, that's how it is. Alternatively, it is a question of finding out 2 displacement functions in a 2-dimensional situation and 3 displacement functions in the case of 3-dimensional situations. So if you write that each point in space has displacement x and y or u and v in the 2 dimensions, then you have to find out u as a function of xy, v as a function of xy, or you have to find sigma x stress as a function of x and y, and then sigma y as a function of xy, and tau xy as a function of x and y. This is 2-dimensional problem. In the case of 3-dimensional problems, you have 6 stress functions: sigma x, sigma y, sigma z, tau xy, tau yx, tau xz. So these 6 stress functions, they are functions of 3 coordinates x, y, z. And in the case of 2 dimensions, the problem can be tackled by Airy stress function approach, which helps us to really simplify the problem in terms of single functions rather than 3 functions of stresses or 2 functions of displacements. And those that stress function again in 2 dimensions can be written in general in the form of 2 analytic functions. Analytic functions are easily constructible and they can be exponential functions involving exponents of z. That's why it is easily constructible, and therefore you try to get the right combinations of these exponential expressions so that it satisfies the boundary conditions of stresses. That will solve the problem. And we have then adopted it in the case of crack problems. Crack problems like center crack problem in plate, and the problem has symmetry, and in that case it is possible that the solution for the problems can be obtained in terms of single analytic function, which is known as Westergaard function. And this Westergaard function was given in the form of just a simple form by Westergaard, and we adopted that Westergaard stress function, and then we got the expression for stresses, and then we are actually we have to now ask the questions: how do we get the displacements? We have got the expressions for stresses in terms of the Westergaard stress function or the symmetric crack problem, but then how do we get the displacement? That's the next question that we should be asking. So we'll now consider how to get the displacements.
Sir,
yeah.
I just wanted to ask one thing, that the Mushkelishvili-Kolosov complex variable formulation defines 2 analytical functions, f, z and chi z.
Yeah.
Those are not directly applied by them to any crack problem, I mean.
Yeah, it can be done. You know that this in terms of this simple crack, which is by having what you call double symmetry, there it has become simplified. But in general, they can be also applied to solve complex crack problems. All types of problems, not only crack problems, also without crack also.
Oh, so the Kolosov work is actually a general mathematical work, or it was in the direction of only fracture mechanics? That's what is my question.
No, okay, that's a good question. You see, question is Kolosov-Mushkelishvili formulation was not referred to crack.
Yeah, that's what I wanted to confirm.
Yeah, they actually tackle the problem of general crack stress analysis. Stress analysis. That's why they define in terms of 2 analytic functions, which makes availability for any applications in 2-dimensional problems. You can have crack, no crack. But then in the case of cracks, in general, that cracks we study, therein, that there are certain simplifications possible, and that's what Westergaard looked into. And then he came out with the simplification that it makes life much easier, and then we can write them in a form which is not going to have infinite number of terms. It is just single term is there, and it helps us to get the solution for stress field around the crack, and that was actually what you call the blessing in disguise. That's all.
Yeah. Thank you. Yeah.
So we just about 1 hour we spent on this part of this discussion, right? Sachin? Hello, Sachin.
Sir.
Yeah.
Sir.
We just about spent 1 hour, right?
Well, actually, we started at 1:15. Therefore, we have spent about 1.5 hours by far.
Oh my God. See, time has gone. So time has gone. So anyway, that I have to then squeeze it a little bit, and I have to make it a little more faster. But I think that let's see how much we can do, because it is certainly new ideas, and obviously all the participants would find it difficult, because I'm not trying to do it, working it out on the blackboard, and students are listening, and it becomes much more difficult job. But unfortunately, nothing better can be done. That the mathematics is a little difficult, mathematics, and also it does not give you time to absorb, because if I write on the board, you will have the time to absorb the things, but you don't have, and I'm unable to, I don't have also the, what you call that, leisure, or rather actually freedom to do that. So therefore, I have to be doing like this, unfortunately. So please pardon me for that nonsense.
Sir, that's okay. In the online mode, I think nothing better can be done.
No, in fact, it is, I think for the participants, you are all teachers, you can appreciate. In fact, this online presentation is a menace, and it does not give students to really listen and see, absorb. That when they hear the lecture, when the teacher is lecturing in the classroom with a blackboard, then he can see the presentation, he can see the whole thing, what is presented, can listen, he can also digest, he has little more time to digest what is going on. But in this online mode, unfortunately, many things are cut off, and it's going fast, and it does not really make it interesting for both sides. Both teacher and taught actually don't enjoy, and I personally don't like it at all, because when I have actually major part of my life I have spent actually lecturing in the classroom, writing on the blackboard, and then trying to present it like a actually PPT presentation. It is like conference presentation. I really find it horrible. It's really horrible. So anyway, please.
You can safely assume that we are all listening.
No, see, the question is that it is half efficient, or more than half efficient, because you are listening, but you don't have time to write, so that you get little more time to absorb, and also to appreciate how they are interconnected.
Yes, sir. Exactly. I was trying to write everything, but it isn't possible. But at least I could write certain things. Yeah.
No, it is just impossible. It is just impossible. Yeah. So that in our Sanskrit they say Shravan, Manan, and Nididhasam. Shravan and Manan. So when we are doing actually classroom presentation, it is both Shravan is there and Manan, little bit of Manan is there. Nididhasam means actually you have to sit down and again rethink, which is not possible, but at least Shravan and Manan is there. But in this case, it is just actually, you just listen, or just listen, that's all. Nothing is there. It is half efficient, or maybe actually less than half efficient. Anyway, so please excuse me for that. I don't have liberty of doing anything more than what I am in a position to do.
No problem.
Now, I would like to say that how do we get the displacement? That's also something quite interesting and involved. But then it is simple in that sense, because a little bit of physics is involved. That all of you know the definition of strain epsilon x. If u and v are the two displacements, then epsilon x is nothing but delta u delta x. So first derivative of u with respect to x. What is u? U is a displacement of a point in the x direction in terms of x and y. And that is nothing but, again, in terms of Hooke's law, sigma x by E minus mu times sigma y by E. Sigma x is the stress in the x direction, sigma y stress in the y direction, Nu is Poisson's ratio, E is modulus of elasticity. So it is nothing but actually Hooke's law, biaxial loading and strain in the x-axis. And now that we have defined sigma x as a function of real part of fz minus y imaginary part of f dash z, so therefore when you plug in, you get this relationship straight. And finally, you see that gets simplified to 1 minus nu by e real part of fz minus 1 plus nu by e y imaginary part of f dash z. So u is nothing but this, and delta u delta x is the definition of epsilon x. So therefore, you see u is what? You must then integrate the right hand side with respect to x. It is partial derivative. So therefore, you can imagine that it is derivative partial. So therefore, the u is going to be integral of this expression 1 minus nu by e real part of f dash z, its integration with respect to x, and then 1 plus nu by e y imaginary part of f dash z. So this product of two functions is integration with respect to x, and since it is partial derivative, we will have a function of arbitrary function of x, a function of y. So we have added on arbitrary functions, and indeed actually this f1y arbitrary function, it indicates generally rigid body mode. When we are interested in just deformation, we don't consider this rigid body mode, we just throw it out. So therefore, you see, noting that z is equal to x plus iy, so dz, when y is not changing, dz equal to dx. So therefore, you see that this dz equal to dx, so therefore this expression, it will finally tell us that u is nothing but integration of this part, real part of fz with respect to x means with respect to z, and this one imaginary part and its derivative again with respect to z. So if we do that, so this function actually becomes, its integration is real part of sigma square root z square minus a square, and this one is actually does not have any effect on the derivative. So this is only derivative of this, this integration will be done, and it will become just fz, and fz is nothing but imaginary part of sigma z by z square minus a square. So that becomes the expression. And finally, if you consider that you are trying to find out the field around the crack tip as z is close to a and z minus a is r for I theta. So if you make all those substitutions, you know, this expression will be easily convertible in the form, this form, and if you just do all that conversion and substitute the value, then u finally comes up to be sigma root pi square root 2r by pi cos theta by 2, and this is 1 minus nu by e plus 1 plus nu by e sin square theta by 2. So that's all it is. And indeed, you know, in this type of expression, one advantage we can derive when we assume plane stress condition, then you know this constants can be substituted by another symbol. This nu and e, all that can be actually converted in terms of modulus of rigidity, and also this nu can be written in terms of one symbol kappa. This is kappa. It looks like k, but it is kappa. Kappa is 3 minus nu by 1 plus nu, and k plus 1 is 4 by 1 plus nu. So with all that thing that you get, you can be written finally in the form sigma root pi a by 2 mu. Mu is rigidity modulus, square root 2 pi by 2r by pi cos theta by 2, 1 minus nu by 1 plus nu plus sin square theta by 2. And again, this can be substituted straight away as kappa minus 1, and this can be rearranged in terms of u is nothing but sigma root pi a by 4 mu square root 2r by pi cos theta by 2 kappa minus 1 plus 2 sin square theta by 2. So this is the expression for u. And now what is v? Epsilon y is delta v delta y, sigma y by e minus mu sigma x by e, again Hooke's law. And then therefore v, we have to actually take the integration with respect to y. So this is how it is. And indeed this is actually a little more difficult because of the fact that your z equal to x plus iy. So when you are trying to talk about dz, x is not varying, y is varying. So dz is equal to I dy, and therefore dy is equal to minus I dz. So therefore you see dx was dz in the earlier case, but in the case of dy it becomes minus I dz. So therefore this integration that is with respect to y, it really have little different way of going about. So let me just get this. Yeah, you see that this is how it is, epsilon y. So therefore, this finally, this different integration is little more involved because you have this integration I dz. So therefore, all that product of two functions and all that can be handled. And once we handle all that, v is going to be given in this form. And again, if we write the solutions for attractive solutions, then in that case you can write z plus a equal to approximately 2a, z minus a as r e to the power I theta. So all that substitution has been made, and finally with little bit of simplification we finally get that v equal to sigma root pi a by 4 mu square root 2r by pi sine theta into kappa plus 1 minus 2 cos square theta. So therefore you see these two solutions look similar. So they involve actually kappa function or kappa symbol and rigidity modulus and r theta. So therefore this is what actually Ewing solution. So finally I have been able to show you how the crack-tip solution was obtained, and it is by this approach. So this is what is mode 1 solution. It has given you solution for stress field sigma x, sigma y, tau xy, and at the same time displacement field. So this is actually what we had for crack-tip solutions, stress and displacement field. So maybe actually it will be nice if you want, if you have some questions at this point, I'll be too pleased to answer them, and then I'll take it up for the things. So this is the mode 1 crack-tip solution, and it is the full thing. And in fact, some of you who are interested, please check, the book that I have given, the book that I have written there. It is written in full form. All steps are that I have written here is there in that book, and therefore it will give you extra pleasure of actually trying to understand and also absorb it. But then it is manageable. But then, with the little bit of ticklish issue, they are product of two functions, and these are complex functions, so you have to do little bit carefully the integration. So that's the only thing is there. Yeah, please let us have some time to discuss on the questions answer. Anything anybody would like to ask? Yes, please. That we have talked about solution for stresses for problems in 2 dimensions. Then we have written the equilibrium equation. Then we have written the problem is statically indeterminate. Then we have overcome the statical indeterminacy by bringing in compatibility conditions, and these compatibility conditions was finally given in terms of displacements. In the case of rigid body problems that you have done, the beam problems in strength of materials, there also you have these compatibility equations, and now here it is compatibility equations at a point. The compatibility equations that you had in strength of materials for the whole body, whereas in this case it is compatibility equation at a point. You have two displacement in the 2 directions, u and v, or x and y displacements, but then these 2 displacements have certain constraint on them, and that's what is compatibility conditions. And in terms of stress displacement, you can write compatibility equation, which can be written also in the form of stresses, and therefore that compatibility equation gives you extra equation to link the unknown functions, and that's what it is. That was used in overcoming the statistical indeterminacy in the case of stress analysis. And finally, the varieties of simplifications and considerations that was adopted in the stress analysis was, firstly, it was that ARE stress function approach, wherein we had to find out 3 stresses, and finally by invoking ARE stress function, we could find out that the problem of 2-dimensional stress analysis is nothing but just finding out one stress function, which is ARE stress function, and it helped to find out the solution of varieties of problems, but then it was not general. Then it was a potential complex variable based formulation of the colossal musculoskeletal, which helped us to solve the problem of any type in 2 dimensions using that approach, which where the stress function was defined in terms of 2 analytic functions, and analytic functions help to obtain solutions of enormous number of problems because of the fact that these functions can be easily written, constructible, and therefore that was the simplification possible. And then coming down to crack problem, it was possible to find out the solutions for the crack tip stress field. It's not the whole body, but this crack tip stress field was obtained very easily by considering the Westergaard stress function approach and simplifying the expressions, and it was possible to write in the form of very simple expressions for the crack tip stress and field. Yeah, that's it. That was what we had done. Please go ahead. And if you would like to ask some questions, otherwise, we'll just about put a couple of minutes break, and then we'll get started in my last lecture of the day, which is again solutions for crack tip stress field in a problem which is little different. How to obtain the solutions for different problems. And in the passing, I would like to say that if it is a mode 2 problem, it is also in a similar fashion you can, I'm sorry, in a similar fashion you can write the Westergaard stress function for mode 2, and that stress function is nothing but it is minus tau z by square root z square minus s square. So this was sigma z divided by square root z square minus a square. In the case of mode 2, the solution Westergaard stress function is minus I tau z divided by square root z square minus a square. And if that solution you begin with and then take the derivation of this, the definition of sigma x, sigma y, tau xy stresses, you can obtain the solutions in a very similar fashion. Yes. Please. Okay, then I will ask you questions. If you are not trying to ask questions, clarification, I will ask you questions. So what is analytic function? What is analytic function? Somebody should answer, please. What is analytic function? We talked about analytic function, analytic functions. What have you appreciated? What is analytic function? Please try. Even if it is wrong, it does not matter. I'll be happy to know that wrong answer also. No answer? Analytic function, what does it mean? Any complex function has 2 parts, real and imaginary. Isn't it? Every function has, complex function has 2 parts, real and imaginary part. And if the real and imaginary part, they satisfy what is known as Cauchy-Riemann conditions. So if they satisfy Cauchy-Riemann condition, that first derivative, say real part derivative with respect to x is equal to y derivative of the imaginary part, and vice versa, that first derivative of the function, real part of the first derivative of the function is equal to minus imaginary part derivative with respect to y. You know that relationship, Cauchy-Riemann condition, and real and imaginary part, they are actually connected by this relationship. They are called Cauchy-Riemann condition. If that is the case, then in that case it states that the real and imaginary part of the functions, they are both solutions of Laplace equation, harmonic equations. Laplace equation is a harmonic equation. So both real and imaginary part of the functions are actually solutions of Laplace equation. In that case, the function is called analytic functions. Okay?
Yes, sir.
Yeah, and what is actually Airy stress function? What is its typicality? What is the typicality of the Airy stress function? You have seen it. I know I talked so much of time on the Airy stress function. What is its typicality?
Sir?
Yeah.
Am I qualified to answer your question?
Yeah, please. I think that you can let them actually also know the answer, and let us see. Yeah.
Okay. The 2D elasticity problem poses itself in the form of determination of three stress functions, sigma x, sigma y, and tau xy. Those three stress functions, with the help of Airy stress function approach, can be converted into determination of just one function which is given by Airy.
That's it. That's it. That means actually all three components of stresses are expressible in terms of one single function, that is the Airy stress function. And this Airy stress function is so defined, it satisfies the equilibrium equations in 2 dimensions, only that it has to actually, to find out it. It is just actually we have to find out phi which satisfies the boundary conditions. That's all. It is one function to be determined, and how do you find out it? It gives you an equation involving biharmonic equations, grad 4 phi equal to 0. So one equation is given which involves that only function phi, Airy stress function, and you can obtain the solution provided you select phi in such a way that it satisfies the boundary conditions. Then it is simply left to determine phi from that biharmonic equation its form. That's all. So it actually makes the life much easier and much easy to handle. That's it. That's what it is.
Yes, sir.